The idea of diffraction is also important for what's called image resolution, uh, because diffraction happens for circular openings as well. So if you have a light source, a point source of light on your retina, it forms an image. And even if the light is a point source, this image has some diameter. And moreover, there is this central bright area, but then there is a dark fringe around it, and then another bright area, dark fringe around it, and so on, right? And as you can see, this equation doesn't quite apply when it's a circular aperture, but the same general relationship does apply, that as this width increases, the theta decreases, meaning this central bright area gets smaller. And so then as you have a bigger opening, as you have a bigger aperture, for example, in our eye, the aperture is the pupil, then you get a smaller bright fringe. And now the reason this is important is that as you get a smaller bright fringe, then something that is actually a point source appears to be more like a point source. So the image then is clearer because it's closer to being an actual size, I guess you could say, and you can get more detail in the image. So that's why some animals, like eagles, are able to see a lot more detail than us. They have bigger pupils, so they're better able to separate objects that are close together. That's the key thing about resolution, is it's how well you can separate objects that are close together. Now, you may have seen this at night. Like I don't know if you've ever looked carefully, but if you see cars driving toward you and you're looking from far away, sometimes it looks like there's just like this one big area of light and there's stuff like there's a big area of light, and then as it gets closer, you're like, oh look, there's two. It's actually a car, and then you get closer and you wind up seeing the headlights. But when you're far away, it looks like those two headlights are a single source. That's because your eyes don't have enough resolution to separate them when the angular distance between them is smaller. When they're further away, there's less angle between the two headlights, and then as they get closer, there's more angle, and then you can separate them out into two sources. Right? Yeah. Now, this central bright fringe, the first dark fringe happens where sine theta is 1.22 lambda over the diameter of the aperture. This is the diameter of the aperture. Yeah, and this is the angle, from straight on. And this 1.22, I looked and I couldn't find a good explanation or come up with a good explanation of where that 1.22 comes from. So for the moment, just accept it, and hopefully I will I will be able to figure out where that came from in time. Now, and again, for the small angle approximation, we can say that this theta is 1.22 lambda over d, if we use our small angle approximation. Now, this leads to what's called, I'm not trying to pronounce this name, it looks like Rayleigh, but it's not quite Raleigh, anyway. This guy's criterion and this has to do with whether we're able to distinguish sources of light. And what his criterion said is that if the first dark fringe for a source of light passes through the central bright fringe of a second source, then we can't distinguish the sources. Okay, meaning that we wouldn't see two distinct headlights on the car, for example. And again, if the first dark fringe happens here, then that means that the minimum angular separation between two objects needed for us to distinguish between them is 1.22 lambda over d. And so we can do some calculations with that. Now resolution is important when you're doing astronomy. You're looking at objects that are very far away, and so you need to have a really as big of an aperture as you can, really, to get the best resolution you can. So you can distinguish, you can distinguish two stars, and we found a couple things called binary stars, where there are two stars that are orbiting each other, kind of really close together, and because the Hubble telescope has such high resolution, we were able to see that there were two separate sources of light. This is also of interest in the art form known as pointillism, which you may have learned about in art classes. But pointillism is just a bunch of different colored dots, and the artist paints entirely with these different colored dots. If you look at the picture up close, it just looks like a bunch of dots and you can't see anything. But if you back up, eventually you get to the point where this Rayleigh's criterion is passed, and the angular distance between between two dots is less than you can resolve. And so, say if you have a bunch of green dots and a bunch of yellow dots mixed in, then your eye, a bunch of blue dots and a bunch of green dots mixed in, your eye just perceives. I keep saying the wrong colors. If you have a bunch of blue and yellow dots together, blue plus yellow is green. If you have a bunch of blue and yellow dots mixed together, then eventually, if you back up further, you'll just see green, because you can't resolve those two different sources. And this is also relevant in television monitors. For a long time, TV and computer monitors have these pixels, and each pixel is a given color. And traditionally, TV monitors only had red, green, and blue, which are the additive primary colors. And so in a region that was, say, yellow, yellow in terms of light is blue plus green. So in a region that was yellow, it might be like each pixel was alternating blue, green, blue, green, blue, green in a grid, and then you just see this yellow color because the sources are too small to distinguish. If you get a magnifying glass or something and look at your computer screen, you might be able to see individual pixels, although I don't know whether there might be too many pixels even for that nowadays. But that's how traditionally colors have been made on television and computer screens as well.